So where does it go from here? What's next for isolation forest and anomaly detection as machine learning continues to evolve? Let's take a look at the future of isolation forest, exploring new research directions, hybrid models, and the next generation of anomaly detection techniques. Anomaly detection is evolving, and isolation forest is just the beginning. As data grows in volume, complexity, and speed, the need for faster, smarter, and more adaptive anomaly detection has never been greater. So, what's next? Where is isolation forest headed, and what are the future trends in anomaly detection? One exciting direction is hybrid models, where isolation forest is combined with deep learning techniques like autoencoders or transformer-based anomaly detection, while isolation forest excels at fast, unsupervised anomaly detection. Deep learning models can capture more complex, high-dimensional patterns. By combining both approaches, researchers are developing ensemble methods that enhance accuracy, reducing false positives, and improving robustness in challenging datasets. Another frontier is real-time adaptive anomaly detection. Traditional machine learning models, including isolation forest, are typically trained on historical data, meaning they can become outdated as patterns change. But in dynamic environments, like cybersecurity, finance, and industrial IoT, anomalies evolve. The next generation of isolation forest models is being designed to continuously learn and update in real time, adjusting thresholds and anomaly scores based on new data streams. This could make the model even more effective in detecting emerging threats, fraud schemes, and equipment failures. There's also a growing focus on explainability and interpretability. One of the biggest criticisms of anomaly detection models, isolation forest included, is the challenge of explaining why a point was flagged as an anomaly. Future versions of isolation forest could incorporate explainable AI, XAI techniques, offering clearer insights into what features and patterns contributed most to an anomaly score. This would make anomaly detection more actionable, especially in industries where human oversight is crucial. Another challenge researchers are tackling is handling extreme high-dimensional datasets. While isolation forest performs well in many cases, its efficiency decreases when dealing with thousands of features. Future developments may include adaptive feature selection techniques that automatically prioritize the most relevant attributes, reducing noise and improving accuracy in massive datasets. And finally, there's the push toward distributed and federated anomaly detection. As more organizations move to cloud-based architectures and decentralized data storage, models need to operate across multiple locations while preserving data privacy. Future versions of isolation forest could be optimized for federated learning, allowing anomaly detection models to be trained and updated across different datasets without exposing sensitive information. The bottom line, isolation forest isn't going away. It's evolving. Faster, smarter, and more adaptable anomaly detection is on the horizon, and isolation forest is at the center of it. Whether through deep learning integration, real-time adaptation, or improved interpretability, the next generation of anomaly detection models will be more powerful than ever. And with that, we wrap up our deep dive into isolation forest. From understanding how it isolates anomalies to seeing it in action across industries, we've explored why it's one of the most effective and scalable anomaly detection methods out there. If you're working with data and need to uncover hidden outliers, isolation forest is a tool you need in your arsenal. So, what's next for you? Are you ready to test it on your own dataset, experiment with parameter tuning, or maybe even integrate it into a live system? Whatever your next step is, one thing is certain: anomalies won't stay hidden for long.